All right, hello everyone. Welcome to the next part of this lecture number 10. In the previous part, we did the functional transform, and in this part, we're going to start the operational transforms. So, again, we are going to take Laplace transforms of operations. For example, if we were to multiply a function with a constant, if we do addition or subtraction of different functions, right? Addition and subtraction are operators. Multiplication is a now operator. Similarly, differentiation and integration are operations. So we are going to find out what the Laplace transform of these operations will be. And practically, we are going to see that the effect of both the time domain and the frequency domain. We can apply these operations for example, in the time domain and see what the effect of it on the frequency domain or on the S domain will be. And then we can practically apply these operations in the frequency domain as well and see its impact on the time domain as well. These are the operational transforms that we are going to consider. In this part, we are going to talk about the multiplication, addition, subtraction, differentiation, and integration. And in the next part, we're going to talk about translation in time domain, translation in frequency domain, and scale changing. So just bear with me. We're going to do these three, 5 to 7, in the next part of the 10th lecture, the same lecture. So let's get started with multiplication by a constant. So here is the Laplace transform that you know, right? So Laplace transform of f of t, which means that 0 negative to infinity, f of t e raised to power minus st times dt, it comes out to be f of s. So the idea is that if you were to multiply this function f of t with a constant k, what would be the Laplace transform of that? It's a constant, so it should come out, because at the end of the day, just imagine that, right? You are solving this integral. So if you have a constant k multiplied over here, right, this k should just simple come out. So that is why multiplication of a constant in time domain, right, should have the multiplication by a constant in the frequency domain. Very simple. So you can just multiply it by the same thing. But it needs to be a constant. It does not need to be, it shouldn't be a function of time. If it's a function of time, right, so that's multiplying two different functions. It's not a multiplication by a constant. The constant comes out of the integral. Now let's do in addition and subtraction. Again, very similar. Consider this integral, right? Again, if in this integral f of t is to power minus st, if let's say if you have multiple functions, f1 of t plus f2 of t plus f3 of t, so essentially you're going to have multiple integrals as well. So it's kind of a very linear operation. So addition and subtraction in the time domain translate to addition and subtraction in the frequency domain. So for example, let's say again, you have, if you were to take a Laplace transform of a function f1 of t, it should come out this. For f2, it should come out this. For f3, it should come out this. So if you were to take a Laplace transform and add the two functions f1 and f2 and subtract the third function f3, the answers should be f1 of s, f2 of s, minus f3 of s. And again, it's exactly solving it, thinking about exactly the similar way, right? So this thing, this entire thing in the integral is going to appear like, right, f1 of t plus f2 of t da 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 e raised to power minus st dt. And if, again, you're going to take this thing out, then you're going to take this thing out, and then it will become multiple integrals. So again, multiple Laplace transforms. So it's a very simple operation. Addition and subtraction just translate very simply. The addition and subtraction in the time domain should become addition and subtraction in the frequency domain. Okay, now we're going to do differentiation and integration. And the answers, although the answers are going to look very simple at the end of the day, but we are going to derive those expressions. And that will be good. Okay, so let's do that. So here's the differentiation. Now you are taking a differentiation of a function f of t, and you want to find out the Laplace transform of the derivative of an f of t. So again, how it looks like, you're going to open up this integral, 0 negative to infinity, put the function, this new function, f of t or g of t, let's call it g of t. Like, let's say this is g of t is derivative of f of t of dt. So anyhow, now this g of t is present over here, e raised to power minus st dt. So how are we going to solve this thing, right? Okay, so this is kind of interesting and very cool to solve. So let's get started in terms of solving it. The very first thing that you need to do is we need to take advantage of something that we call as integration by parts, right? Do you remember the product rule of differentiation? So this equation is derived from the product rule of differentiation. When we take a differentiation product rule, if you have two functions, let's say u and v, and you take a derivative of these two functions, right? So how do you do that, right? So you, for example, for u and v and the derivative, first you get u derivative of v plus v derivative of u. If you get to solve that and then rearrange that equations and then take an integral, maybe I should do that sometime. So for example, if you are unable to drive this equation, just ask me, I can drive this equation for you. It's like literally a two-step, and it is based on this again product rule of differentiation. Sorry, right? Let me write it down. Coming from product rule from differentiation. Shouldn't take more than two steps. Do it and get back to me if you cannot do it. Anyhow, so this is, you can practically use this equation to evaluate if you have multiple functions appearing in the within the integral, right? So I am gonna kind of use this equation here. Okay. So let's see. So I have two things over here, right? So I am going to compare this with this entire thing. Okay. So let's see now. I am gonna call my u as e raised to power minus st, and then I'm gonna call my dv as the derivative of f of t over dt times dt. Okay, nice. So I got both of these things done, right? So I kind of decompose this integral into these parts, right? So now I'm going to kind of solve these things, and I'm going to evaluate it with respect to this. So I already know the value of u. I need to find the value of v, and I also need to find the value of du. Okay, so maybe let's start with finding the value of dv. Let's find the value of the v. We already have a value of the u. Let's find the value of the v. Okay, I can find the value of the v by taking again an integral on both sides, right? Integrate both sides by t. If I were to integrate both sides by t, right? Integral of dv equals integral of, and the derivative of function with respect to dt. You can practically cancel this thing out, and your function is going to be left with v equals f of t. Nice. Okay, very simple. Cool. Now I want to do, so I got a v. Integral is here. I already know the v. Let's find me du, right? And u is here. So I'm going to take our derivative of this thing with respect to t, of this function with respect to t. So du by dt comes out to be again minus 1 over s e raised to power minus st. Oh, sorry, not minus 1 over s. I'm not taking an integral. So it should come out to be minus s. Minus s e raised to power minus st. Okay, so this is the derivative. And of course, I need a du exactly. So du should be minus s e raised to power minus st times dt. Okay. So I got all the three things. I got the u, I got the v, and I got the du. And I'm going to replace all of them back into this big one equation. Okay. So again, let me write this equation maybe again. Integral of u dv equals uv minus integral of v times du. And this was Laplace transform of derivative with respect to t of f of t, right? So I'm going to do multiplication of u and v. U was e raised to power minus st, and v is f of t, right? So we have f of t e raised to power minus st. And again, while I was deriving these equations, right? So for example, while I was taking these integrals over here and finding the value of the v, I kind of ignore the limits of integration, but eventually those limits of integration needs to be applied over here, 0, negative to infinity, just to find those expressions, right? And then, so u is f of t e raised to power minus st, 0, negative to infinity, and then minus integral, again, 0, negative to infinity. What is v? V is f of t. F of t times minus s e raised to power minus st times dt, which is du, and du is this thing. Okay, nice. Okay, I got it. Okay, so this is interesting. Now let me solve for this thing. Why don't I solve for this thing like separately? Let's first consider this thing, right? So you have f of t e raised to power minus st, 0, negative to infinity. Once you're going to put infinity over here, right? Let's say infinity over here in time. So e raised to power minus infinity is 0. Practically, you're going to get 0. 0 multiplied by f of t is going to come out to be 0, which is essentially you're applying a limit t approaches to infinity to this function. Minus, let's put now 0 over here. If I'm going to put 0 over here, it is going to come out to be e raised to power minus 0 times f of 0 negative, right? So this should come out to be minus of e raised to power minus 0 is 1 minus f of 0 negative. Okay, so the first term comes out to be this. Now let's look at this term, second term. Maybe I can do the second term here. Okay, second term is interesting and very simple. 0, negative, infinity, f of t minus s e raised to power minus st dt. Very, just take the constant out, minus s. So you are left with minus s, 0, negative to infinity, f of t e raised to power minus st times dt should be minus s f of s, right? This entire thing is f of s, Laplace transform of a function f of t. Okay, this is like super simple. Just replace this value and replace this value back into this equation. So your Laplace transform of the derivative of f of t should come out to be this first expression, minus f of 0 negative, minus this expression, minus s f of s. So this should be f of s minus s f of s minus f of 0 negative. Nice. So this is a Laplace transform of a derivative of a function where you have to use this rule of integration by parts. I'm going to apply the same rule when I'm going to do in a second about when we are going to do the integration in operator as well. So anyhow, this is how you can derive it. So derivative of a function of f of t comes out to be s f of s minus f of 0 negative. Now let's get started and look at, so this is what we just derived, right? Here's our derivative of f of t, s f of s minus f of 0 negative. Another important thing to consider over here, to look over here, is this entire derivative operation just becomes some sort of an algebraic operation in the frequency domain. So that's kind of one of the powers of Laplace transform, that your integrals and differentiation operators comes out to be simple algebraic equations in frequency domain. Okay. So before we do the integration, I want to do quickly do one more thing, which is a higher order of derivatives. So we just did that first derivative of f of t. So what is going to happen if I'm going to take higher derivatives of f of t, second derivative of f of t, or third derivative of f of t? Why? So if you remember your second order circuits, where you get a second order differential equation with a double derivative as well. So maybe it's useful to see how to find out higher order derivatives in Laplace transforms. Okay, so let's again consider a function f of t. and we are interested in finding a higher order derivative of f of t. Okay. So I'm going to start with saying that this first derivative of f of t that we just calculated here, right? So this function is g of t. I'm just defining it, so eventually I'm going to take a derivative of g of t, which is going to be a second derivative of f of t. Okay, so g of t is derivative of f of t, and we just evaluated that, right? So this is g of t, right? So Laplace transform of g of t should be g of s. So that is why you have g of s over here. And again, essentially what g of s equals to is the derivative of f of t over here, which we have just evaluated, and it should come out to be equals to this. So again, we already know that this is the first derivative of f of t, the answer for the first derivative of f of t. However, why I just made this into another, represented this by g of t is because this is going to make my life easier, because I'm going to take now a derivative of g of t, which is going to be a second derivative of f of t, right? So if you're going to take a derivative of g of t, it should be a second derivative of f of t. Okay. So practically now I'm going to do a Laplace transform of a derivative of g of t, which should be a second derivative of f of t. But interestingly, if you can see it over here, right, I can easily do that by using this equation, right? S of g of s minus g of 0 negative. Nice. So I already have a solution for that. I don't need to do the whole thing again. But now but what I'm going to do is I'm going to replace this g of s over here to find the final equation. Okay, so let me do that very quickly. Or maybe I can just I can just do it over here, right? So Laplace transform of derivative of g of t with respect to dt should be, again, I'm using this equation, s of g of s minus g of 0 negative, and I know g of s is this, s of f of s minus f of 0 negative. So I'm going to replace this over here. Laplace transform of derivative of g of t is s, g of s is s, f of s minus f of 0 negative minus g of 0 negative should come out to be s square f of s minus s f of 0 negative minus g of 0 negative. Okay. So this is, but I want to represent, since I said that my g dash of t is the derivative of g of t, and the g of t was a derivative of f of t, so it is going to become d square by dt squared of f of t, right? So practically I want to define everything in terms of f of t. So I already have f of s here, f of 0 negative here. I'm going to replace this g 0 negative term. So again, Laplace transform of first derivative of g of t is Laplace transform of a second derivative of f of t should be equals to s squared f of s minus s of f of 0 negative. What is g? Again, g of t equals the derivative of first derivative of f of t. So I am going to call this as a derivative of, so I'm replacing this term over here, right? F of 0 negative. So this is the first derivative of f of 0 negative. So I can replace this entire equation with this. So what did we kind of learn? I'm going to show you the nth representation in a second. Is if you are taking a double derivative here, right? Okay, in this equation, when you are taking a single derivative, your equation was s f of s minus f of 0 negative. Once you are taking a second derivative now, here is the second derivative, you get an s square here, f of s remains the same, you get 2 minus 1 here, f of 0 negative is the same, right? And then you get the derivative, which is going to come out to be n minus 2. Is it? Yes, I'm going to talk about it in a second because we got like this one extra term here. Okay, so I'm going to show you my nth representation in a second now. So if you have a function with an nth derivative, what its function is going to look like, Laplace transform, and it is over here. Let me rewrite the other one as well, so I can kind of compare the two. Right, so Laplace transform of double derivative of f of t equals to s squared f of s minus s of f of 0 negative minus the derivative over here, f of 0 negative over dt. Okay. So again, if you are taking an nth derivative, right, so this first term is going to have an Sn, right, so square is going to have a square, and then the rest of the terms is going to be first at f of 0, then first derivative, then the second derivative. And for example, over here, the second term with a minus sign should have s of n minus 1, so 2 minus 1, and then f of 0. Since we just have 2, so we are kind of left, our s terms will go away, otherwise we're going to have another s terms. And then we're going to have s of n minus 2 and this. So s of n minus 2 is over here 2 minus 2, s of 0, which is 1, so we got 1, and df 0, 0, negative, and dt, and this is where we stop. If we would have a higher power, let's say if we are doing a third derivative, then we're going to get here one term as s times of df 0 negative over dt, and then we should get one more, just one, d squared of f of 0 negative over dt. So these terms will continue to keep coming up depending on the higher and higher derivatives we are taking. Okay, so hopefully this should help. You don't need to remember all of that. Ideally, yeah, it's no rocket science here, so maybe you should remember some of this. At the end of the day, you're going to have the tables available, and you should remember some of the things, and the rest of the things should be the formula sheets. Very quickly before we finish the lecture, let's do the integration as well. Now I'm interested in finding the integral of f of t, the Laplace transform of the integral of f of t. So again, here is a function, original function f of t. I took an integral 0 negative to t of that function, right? And again, since your limits of integration had a variable t, so I ended up replacing the variable of integration with x. And I'm interested in finding the integral of, again, f of t. So again, this entire function is going to appear in the integration over here, and then e raised to r minus st dt. Whenever I'm going to come across this thing, I have to solve this entire thing by parts. So let's do this thing again. Let me define what the u is, what dv is, and then find the values, right? Okay, so let's see what okay. So I'm going to call my u as this integral. So u should be equals to 0 negative to t f of x dx. And then I'm going to define what my dv is. My dv should be equals to this part, the other part, this part, e raised to power minus st times dt. So I already know the value of the u. Let me find the value of the v first. Okay, in order to find the value of the v, again, I can integrate this. Integrate by t. So if I'm going to integrate by t, integrate dv st times dt should comes out to be, again, yeah, okay, so this dv should come out to be v equals minus s e raised to power minus st minus 1 over s e raised to power minus st. So this is v. So I ended up finding the value of u was already here. This one, v was here. I have v. Now I need to find du. Okay, so I have to take a derivative of this equation. So if I'm going to take a derivative of this equation with respect to t, right, d by dt, we're going to have an integral 0 negative to t and f of x ds. Again, this f of x dx was originally it was f of t, but due to the changing of the limit of integration, since our limit of integration has a variable t, so we end up changing the variable of integration to x, right? So over here we can see that if you're going to take a derivative of this integral, it should just come out to be the function itself, right? And of course with sorry, I know what happened. Just give me 1 second. Here are we. Okay. Right, so this should come out to be, entire thing should come out to be f of t, so your du becomes f of t dt. So what I'm going to do now is I have everything to put down into this equation. And I'm going to write down all the things here. Okay, so let me do that very quickly. So the equation was integral of u dv equals uv minus integral of v du. And integral of uv is the Laplace transform, as we did that, right, of the function 0 negative to t f of x dx equals to u. What is u? U is again this, v is this, and du is this. Okay. So let's define it again. U and v. So u was your sorry, what is u? I forgot. Integral. Integral 0 negative to t f of x dx, right? And then our v was minus 1 over s e raised to power minus st, and this both should be computed again at 0 negative and infinity, and then negative integral of v what was v? Minus 1 over s minus 1 over s e raised to power minus st times du, and du was f of t dt. F of t dt. So the great thing about this thing is, because now once I'm going to do this expression, I can already see that this term and this term is going to make my life easier. So let's look at both of these terms. So for example, let me look at this term first, right? So this term is 0 negative to t f of x dx, and then the second term over here is e raised to power minus st over s. And both of these terms are being computed at 0 and infinity. Once you're going to apply infinity over here, right, we can see that e raised to power minus infinity is 0. This is going to make the whole term 0. So we're going to get 0 minus. Let's apply 0 now. If I'm going to apply 0, right, so just imagine that if I'm applying 0 over here. If I'm taking an integral of anything which has both lower limit of integration and the higher limit of integration exactly the same, the answer should come out to be 0. So it should be 0 minus 0 should be equals to 0. So I'm kind of left with this, the second part. So the second part is 0 negative to infinity minus 1 over s e raised to power minus st f of t into dt. So once I will do that, I can see that 1 over s should come out 0 negative to infinity e raised to power minus st f of t times dt minus 1 over s f of s, right? So this entire thing is just f of s. And I can replace this entire thing back to original equation here. Laplace transform of 0 negative to t f of x dx, after doing a lot of this integration by parts and this kind of a easier calculation, it comes out to be 0 minus 1 over s f of s. So it should be f of s over s. Beautiful. So your integration in the time domain become a simple division by s in the frequency domain or in the S domain. So again, making the point here again that your complex integrals and differentiations become simple algebraic equations in S domain. So we're going to kind of finish the lecture here. We have a couple of other transforms to do in the next part of the lecture, and that should be the end of things. So I will talk to you in the next part. All right, thanks, bye. Have a good day.